Hello everyone, and welcome back. Today we're going to continue our exploration of the simplex method, which is one of the most famous techniques and algorithms used to solve linear programming problems. So let's assume that you're interested in working with this particular linear programming problem, where we seek to maximize the functional f of x is equal to x1 plus 2x2 plus x3 plus 5x4, subject to these two constraints that x1 plus 2x2 plus x3 plus x4 is less than or equal to 50, and 3x1 plus x2 plus 2x3 plus x4 is less than or equal to 100, with x1, x2, x3, and x4 all restricted to be non-negative. So, as you should already know, the simplex method mandates that this linear program be placed in standard form. So since all of our variables are restricted to the positive domain, we don't have to change anything there. But we do have these less than or equal to inequalities, and we need to change them to equal signs, so we have to introduce two select variables. And we have a maximization problem, therefore we need to negate this and shift it into a minimization problem. So let's just go ahead and write that. So the standard form for this linear program is given to be the minimization of the functional minus x1 minus 2x2 minus x3 minus 5x4 subject to the following constraints: x1 plus 2x2 plus x3 plus x4 plus our first slack variable s1, and that's going to be equal to 50. And then we're going to have 3x1 plus x2 plus 2x3 plus x4 plus our second slack variable, and that's going to be equal to 100, with the restrictions that x1, x2, x3, x4, s1, s2 are all greater than or equal to 0. And we can technically put some placeholder coefficients for 0, s1, and 0, s2 up into our objective function for which we seek to minimize. So once we have our linear program placed in standard form, then we can create what we call the initial tableau for the simplex method. So the initial tableau, L-E-A-U, which I'm just going to abbreviate as T sub 0, is given to be the following. So the initial tableau is given to be, so we have our variables x1, x2, x3, x4, s1, s2, and then we have our constants b, and then we have our objective function in minimization form with -1, -2, -1, -5, 0, 0, and initialization at 0. And then we have our outgoing variables s1 and s2. And then for the first equation we have 1, 2, 1, 1, 1, 0, and that's going to be 0, 1 by default. And then we're going to have 3, 1, 2, 1, with constants in b of 50 and 100. So that is our initial tableau, and some people will write a line between your constraints and your objective function. So that's the initial tableau. That's always the way that we're going to start a simplex method algorithm. So of course, keep in mind what the simplex method does is it cycles through the basic feasible solutions in an optimal way, right? So it looks for the direction that is pointing to the optimal solution, provided that the optimal solution exists. So it starts off the sequence with the basic feasible solution by treating S1 and S2 to be the basic variables. So if that's the basic variables that we're working with, then the initial solution that it proposes to be the optimization of our objective function, which it typically is not, but it starts there, is going to be equal to what? So x1, x2, x3, and x4 are going to be initialized to 0 because they're going to be our null variables to start. And then we have s1 and s2, which are defined to be equal to 50 and 100. And one can show that when we plug in this solution into that objective function, we actually will get 0. Okay? Now, is 0 the largest value for which we can have? Most likely not, right? So our goal is to find the optimal solution. So we could plug in all of our basic feasible solutions and see which one is the greatest, but even then we're not guaranteed that the optimal solution is one of the basic feasible solutions. But if we would want to, start with that perspective, well, how many basic feasible solutions will we have to check? So there are going to be at most, so this is going to be a combination. So notice that we have 1, 2, 3, 4, 5, 6 columns, and then the number of rows that we have is going to be equal to 2. So we have 6 choose 2, which we know is going to be coming out to 15. Other basic feasible solutions, to check, right? But the simplex method typically takes a lot less iterations than the maximum possible C n choose m, right? Where n is the number of columns and m is the number of rows, right? Which is a very good thing, which is why we usually go through the simplex method, because it's actually optimal in a lot of sense. So keep in mind, for the general process for the simplex method, we can typically write all standard form linear programs in the form the minimization of some functional f of x is equal to ctx, subject to the constraints that ax is equal to b with the x vector greater than or equal to 0. But if we want to look at this world from, for example, a theoretical perspective, and we know that the basic feasible solutions is a starting point, how can we write this standard form linear program in terms of the basic and non-basic solutions? So, if we know that x is partitioned into xb and xn, the basic and non-basic variables, and A is partitioned into a basic and non-basic matrix, therefore we can write this in equivalent form. So this is equivalent to the following linear program. So again, we're going to be interested in minimizing. So x is going to be partitioned into xb and xm. So we can write this, for example, as cbt times xb plus cnt times xm, subject to the following constraints, that bxb plus nxn is equal to b, with the restrictions that xb is greater than or equal to 0 and xn is greater than or equal to 0. So that is the partition form in terms of basic and non-basic variables and basic and non-basic matrices b and m. And just in case you are unsure about those coefficients, those are just the coefficients associated to our basic and non-basic variables that we have chosen for a particular iteration of whatever method we're working with. So now we know how to at least start the simplex method. Now let us briefly introduce a couple theoretical concepts that are actually associated to why the simplex method works and how to determine when the simplex method actually has generated the optimal solution for our linear program. So in order to do that, we need to introduce a bit of computational machinery. So definition. So suppose that x star is a particular basic feasible solution of the linear program that we are working with. Then the reduced cost vector, so the reduced costs vector, which we're just going to be abbreviating by R sub m, and it'll be clear eventually why we use a subscript of n, not a subscript of, say, b or something like that, is given by the following vector. So Rn is going to be defined to be equal to Cn transpose minus Cb transpose times the basic matrix B inverse times the non-basic matrix n. And you should be able to verify a couple properties associated with this particular vector. So let's just mention a couple notes here that you may want to investigate on your own, just in case you have the time. So the first thing that you should note is that x star is a basic feasible solution. If this is true, then the determinant of the associated basic matrix B is not equal to 0, implying that the inverse will exist, right? And we're assuming that x star is a basic feasible solution. That means the associated basic matrix is invertible. Therefore, this expression will exist. Now you may want to investigate, for example, the dimensions of each of these vectors and also investigate the dimensions of what Rn should be. But another thing that you should maybe think about is, well, if x star is partitioned into, for example, our associated basic variables for x star and our associated non-basic variables x star n, then you can also show that x star b will be equal to b inverse b, and also x star n will be equal to 0, where 0 is the associated 0 vector associated to, for example, n. Right? So those are just some of the basic observations that one could easily make. Now, what is so special about the reduced cost vector, and how does this sort of relate to the optimal solution for a linear program? So let's introduce the next very important theorem. So let's assume that Rn, the reduced cost vectors, is greater than or equal to 0 for some solution, our basic feasible solution x star, with partition variables x star b and x star m. Then x star is an optimal solution for the linear program. Right? So if you have a basic feasible solution x star that generates a reduced cost vector that is always non-negative, then that suffices to show that x star actually is an optimal solution for the linear program, which is what we're actually going for, right? So let's see if we can go ahead and maybe prove this very important result. So since we know that ax is equal to b, right? So we're going to be assuming that our linear program is in standard form, and we know that a can be partitioned into the following form: bxb plus nxm is equal to b. What we can do is we can actually solve this equation for xb by first off subtracting by nxn, and since xb is our basic variable, the inverse of b is going to exist. So we can write xb to be equal to the inverse of b times little b minus m xm. And you should be able to verify that the dimensions of that matrix is also matching. So since our objective function, which in an original form is ctx, can be decomposed into the form cb transpose times xb plus cn transpose times xm, what we can do is we can replace xb with this expression for which we have right here. So that's going to give us what? So that means that f of x is equal to ctb times b inverse times b minus nxm plus cn transpose times xm. So now what we can do is we can distribute this quantity to b and also nxm, and then we can regroup in terms of xm, because notice we're going to have two xn terms, so we can factor xn out of the right hand side of those two terms once we get them together. So we can write our objective function that we seek to minimize in the form ctb times b inverse b, so that's going to be the first term once you distribute, and then we're going to have plus ctm minus cbtb inverse n, so some slight rearrangements there, times xn, right? We usually like our negative terms to be on the second term and not the leading coefficient term. So once we have this, what do we have? Well, this vector should look familiar. That's precisely our reduced cost vector. So therefore, our objective function can be written in terms of our reduced cost vector, in particular ctb times b inverse b plus rm times xm, right? So that's a very important statement. Now, what does it mean if Rn is greater than or equal to 0? How does that imply that our solution, for example, xb star, is truly an optimal solution? So let's get into that piece. So since b inverse b is going to be equal to xb star, and we also know that f of x is equal to ctx, that means what? That means CTX is going to be equal to, well, keep in mind, f of x can also be represented as that expression there. So CTX is also going to be equal to CTB times B inverse B plus Rn times Xn, but B inverse B is also equal to XB star. So we can write that also as CTX is equal to CTB times XB star plus Rn times Xn. So what we can do is we can solve this equation, for example, Rn(xn), and we can have the expression that Rn(xn) is going to be equal to CTX, that's multiplied, not subscript, so C transpose X minus C transpose subscript B times X subscript B transpose, right? So what do we know about xn? So we know that xn is greater than or equal to 0 because that's one of our two restrictions for our standard form, because we know if x is greater than or equal to 0, then any partition of x will also be greater than or equal to 0 as well. So what can we say about, for example, Rn? Well, xn by default is always going to be positive. Rn is not always going to be positive. So we know that Ct times x minus CTB xb star, which is again equal to Rn times xm, is always going to be greater than or equal to 0 if and only if Rn is greater than or equal to 0, right? That is, the sign of the left-hand side of this equation depends only on Rn because xn is always greater than or equal to 0, since we're assuming our linear program is in standard form, since our goal is to develop some theory for the simplex method. So what is so special about that? So if we write that in alternative form, in particular that thing is greater than or equal to 0, and shift that to the right-hand side, then that gives us that CTX is greater than or equal to CTB times XB star, right? So that is true if and only if Rn is greater than or equal to 0. Agreed? So what is x? So x, keep in mind, is belonging to the feasible region. So if that is the case, we can also write this in a mirrored format, in particular CTB times XB star. Keep in mind that's just going to be equal to f of XB star, and that's going to be less than or equal to CTX for all x in our feasible region, right? So keep in mind we have that f of XB star is less than or equal to f of x for all x in f. And keep in mind, for our linear program, our goal is to minimize f. And we have that since xb star is a particular basic feasible solution in f, and that this is less than or equal to f of x, that means f of xb star is the minimum value for which f can take. That means xb star is the optimal solution if and only if the assumption Rn is greater than or equal to 0, right? And that is a very, very beautiful and very important result, right? And also keep in mind of, in case you haven't already done so, about what Rn actually is. So notice that each row of Rn actually is associated to a variable. Why is my letters blurring together? So variable m xm. And I'll leave it to you to verify that that actually is the case and why that actually connects to this particular important result. So now that we have that very important theorem proven for the simplex method, now let us sort of go back to our example that we were working with and sort of see how this connects. So keep in mind, we will have an optimal solution as long as CTX star is greater than or equal to 0. So that is when we have some basic variables located over here, and we have these numbers here, and they are all non-negative, then we have our optimal solution. Notice that we have some constants, -1, -2, -1, -5, and we have to turn all of them positive in some way. Once we do so, then we're going to have our optimal solution in front of us, all right? So keep in mind, How are we going to do that? Well, should we focus on -1, -2, -1, or -5 first? So now let us introduce the next theorem that is going to guide us with some strategies of which one we should focus on. So improvement on the value of xx will be guaranteed if what? Because right now we have a value of 0. If we choose, for example, x1 as our first pivot, it might make our optimization value worse and not closer to the highest value for which this row can be, which of course is equivalent to the minimization value, right? So we can actually guarantee an improvement of the value of f of x if we choose the minimum where k belongs to, for example, b, of the quotient bk ajk. And keep in mind, b corresponds to the basic variables in our current state of our Tableau. In our case, that's going to be equal to S1 and S2 for our particular example. So what we want to do is we want to find the minimum value of the ratio amongst each of those particular negative values. So the only values that, again, we need to focus on are going to be the ones that are currently circled in red. So the strategy is to choose the one that is most negative because we need to make all of them positive. So once you choose, for example, the most negative variable, right? So in this case, we see that x4 is going to be our entering variable. What we need to do next is then calculate our ratios for that particular column. So we need to do, for example, bk divided by ajk, and we also need to do 100 divided by 1. And then we need to choose the one that generates the minimum, and that's going to determine which variable is going to be the departing variable. So in our particular example, that means we need to choose, for example, the minimum of 50 divided by 1 and 100 over 1, which is going to be equal to the minimum of 50 and 100, and the minimum of 50 and 100 is equal to 50 for our particular example. Therefore, this particular row is the row that we're going to focus on, so that means that S1 will be our departing variable. And I'm not going to prove this theorem, but every time you choose that particular one, the value of f of x is guaranteed to be better than what it used to be. So now what we need to do is we need to turn this particular value into a pivot, which means we need to turn that -5 and that 1 above and below it equal to 0, and then make sure everything is balanced around it via Gaussian elimination. So if you have that system written down, what we can do is we can do, for example, 5 times row 1 plus our 0 to generate a new 0, and we can do row 2 minus row 1 to generate a new row 2. So once we have that, then we have the result of the first iteration of the simplex method, which I'm going to call as the T1 tableau. So T1 again is going to have x1, x2, x3, x4, s1, and s2, and finally b. And then we have z. And then remember we had x4 enter and s1 depart, so we're going to have x4 and s2 there. So once you actually work through this Gauss-Jordan elimination process, you should get 4, 8, 4, 0, 5, 0, and 250. Keep in mind, if that did not go up from 0, you chose the wrong pivot, because if you follow this particular theorem, that value will always improve, right? Very, very important. So, and for our coefficient matrix, we're going to have 1, 2, 1, 1, 0. 1, 2, 1, 1, 1, 0, 1, 2, 1, 1, 1, 0, and 2, minus 1, 1, 0, minus 1, 1, and then 50 and 50. Okay, now notice that we've only done one iteration of the simplex method, but notice that all of the coefficients here are positive, right? So that means we have x4 equals to 50, S2 is equal to 50, and since all our coefficients in our first row is all positive, that means what? That means we've found our optimal solution. So that means our optimal solution, x star, is going to be equal to x1, x2, x3, x4, s1, and s2, right? With a maximum value of 250. Right? And that is the simplex method. Now, before we go, I actually want to do one more example because there's one special case about the simplex method that I have yet to introduce. Consider this example, where the function we seek to maximize is f of x is equal to 4x1 plus 2x2, subject to these two constraints, minus x1 minus x2 less than or equal to 12, 3x1 minus x2 less than or equal to 15, with x and 1 being non-negative. So if this is a two-dimensional problem, you can probably solve this problem graphically if you really want to. If you really want to, you should be able to verify that the graph of this particular feasible region is actually going to be looking like this, right? So this is going to be equal to f. So again, if we seek to optimize some two-dimensional functional, which keep in mind, since this input is two-dimensional, that's going to be pretty much a third-dimensional output. So we want to sort of maximize that surface over that particular region. So if we draw this in a different way, for example, our goal is to optimize, for example, this particular 3D function that's sort of floating above that, right? And if you sort of think about this from a three-dimensional perspective, that line should be always increasing, and since the area underneath it is always going all towards infinity, there will be no optimal value for this particular function. But if you do not want to sort of think about that, nonetheless, you should observe that this set f is unbounded. So if the set f is unbounded, it's not guaranteed that the optimal solution to this linear program exists. That's one of the important things we come across in the fundamental theorem of linear programming. But how would you pick up on that if you don't want to think about this geometrically and you just want to use the simplex method to solve this? So let's actually walk through that and see what we actually get. So our initial tableau for this particular problem is going to be equal to what? So if we change this to a minimization problem, that's going to be equal to what? So we have x1, x2, we're going to have two slack variables s1, s2, and let's put our b column there. So our z is going to be changed to -4, -2, 0, 0, default 0. And then our departing variables that we want is going to be equal to s1 and s2 with coefficients -1, -1, 1, 0, and then 3, -1, 0, 1 with b values 12 and 15. So that is our initial tableau. So how do we go about this using the simplex method? So the first thing is to identify the most negative coefficient in z because we want all of these to be equal to positive numbers. So we're going to probably have at least one iteration. If we can make those both positive on the first iteration, that is of course ideal. So once we choose that particular column, we have that x1 is going to be our entering variable. Now we need to choose our departing variable. So what we need to do is what? So we need to do, for example, 12 divided by -1 and 15 divided by 3 and choose the least non-negative ratio amongst those two. So our ratios for this particular iteration is going to be 12 divided by -1, so that's for S1, and then 15 divided by 3, right? So 12 divided by -1 is going to be equal to -12, and 15 divided by 3 is going to be equal to 5, and 5 is going to be the least non-negative ratio. Least non-negative ratio. So if that is our least non-negative ratio, that is going to be the row, and 3 is going to be our pivot. So that means we need to change -1 and -4 to 0. We need to depart S2 and enter x1. So via Gaussian elimination, one way we can do that is, for example, 3 times row 0 plus 4 row 2 to get a new row 0. That's going to cancel out that -4. And then we can do 3 times row 1 plus row 2 to generate a new row 1. And then we can, for example, divide that last row by 3, but we don't like usually having fractions there, for example. That's going to give us -1/3, that's going to give us 1/3. We might want to wait until the last part of our iteration before we start introducing fractions, but that's just a preference, nothing required there. So once we go ahead and perform those 2 steps or possibly 3 steps of the Gaussian elimination, we're going to have the result of the first iteration of our simplex method, whose tableau is going to be represented by t1. So again, t1 has the same base variables x1, x2, s1, s2, and of course we have our column b, and then we have our 0, and then we have our s1, and then our new basic variable x1. Okay, so of course z will come out to 0, minus 10, 0, 4, 60. Keep in mind that number will always be better than it used to be, provided you choose these particular directions. And then 0, minus 4, 3, 1, 51. And lastly 3, minus 1, 0, 1, and 15. So we have not found an optimal solution via S1 and X1 because notice that we still have some negative coefficients located in our CTX row. So we need to focus on this particular column. So x2 is going to be our entering variable, and one of these variables should be our departing variable. And how do we choose our departing variable? We need to calculate our ratios. So our ratios for this are going to be equal to what? So we're going to be doing 51 divided by minus 4 and 15 divided by minus 1. So once we do that, we're going to have 51 divided by minus 4, that's going to be negative 12.75, and that's going to be equal to negative 15. So which one do we choose? We choose the least non-negative ratio. But what do we have here? All are negative, right? All are negative, or pretty much all are, actually that's probably not the best way to think about this. None are positive. It's sometimes the case where you have, for example, you're divided by 0, and of course that could be positive infinity, but none are positive, right? So if none are positive, that means there is no replacement variable, right? And that's a sad thing, right? So our entering variable will be x2, but there is no variable for which it is to replace, right? So here's the last theorem that I want to leave you with when it comes to the at least basic form of the simplex method. So if the replacement ratios, that's what we're calculating over here, do not have any positive values, then the simplex method implies that f does not have an optimal solution due to unboundedness. So you can use the simplex method to determine whether or not the function is unbounded, which of course results in a potential lack of an optimal solution. So those are the basic principles associated to the simplex method. So at this stage, regardless of the linear program, you should be able to use the simplex method to find the optimal solution, provided that the optimal solution exists. So I hope you enjoyed, and I'll see you in the next video. Take care.